Okay, are we back?
Yes, seems
Okay.
now we got all back. Very good. Yeah, it's 1 minute past 9. And so let me start the session. We are here today on the session number 07A, Observing Gravitational Wave from Space, Instrument Science. And my name is Sarah Paskowski. I'm working at the AI in Hanover, and I have the honor to chair this session. And now let us start right away with our first speaker, Ms. Ana Pérez Ortega, and I'm very sorry if I pronounce your name incorrectly. Please, Ana, go ahead. The stage is yours.
Well, hello everyone. My name is Ana Pérez, and today I will talk about a project we are working on called a magnetoresistive based high precision magnetic diagnostic subsystem for LISA. And this project is underway at the Institute of Space Science of Catalonia. And here I show a breakdown of the presentation, where first of all I will make a brief introduction of our group, and then I will show a quick overview of the Spanish contribution at LISA. Then I will show up the requirements for the magnetic diagnostic subsystem and the technology we propose for LISA based on anisotropic magnetoresistive sensors, from which I will show some characteristics such as sensitivities, power dissipation, and that stuff. Later on, I will show the magnetic setup we work with and the latest results we obtained and conclusions on further work. First of all, the gravitational astronomy group of the Institute of Space Science provided the data and diagnostic subsystems of LISA Pathfinder, a precursor mission launched in December 2015 that successfully demonstrated key technologies. Now this group leads the Spanish contribution to LISA, and is called Scientific Diagnostic Subsystems. These provide several diagnostic sensors that monitors the environment all around the spacecraft and the test masses with high precision. Here is an overview of the SDS, and the national contributions are the ones shown on the top of the slide, where we are the science diagnostics system. Our system is in charge to characterize and monitor the thermal environment on the all around the spacecraft and the magnetic and radiation environment surrounding the test masses. In addition, it is in charge to generate science data information during the science mode. On the flock schematic view, we can see that the DACU is the core of the system, which is the control unit, and it's in charge of communicating with all the sensors all around the spacecraft to monitor the environment. But we will focus on magnetometers. And here I show the magnetic diagnostics requirements that were set by the precursor mission LISA Pathfinder. On the graph shown are the results of LISA Pathfinder, and the interplanetary magnetic field detected was about 100 nanoteslas around the 0.1 millihertz. So we have a stability requirement of 10 nanoteslas root hertz around the 0.1 millihertz to make sure we detect all the fluctuations on the environment. And the volume of the diagnostic subsystem, the magnetic diagnostic subsystem, has to be less than 35 or per 83 per 32. The maximum power dissipation for each sensor has to be less than 20 milliwatts. The maximum mass has to be less than 100 grams, and the results shown on the plot were obtained using, well, on LISA Pathfinder, they used triaxial flux gates, but they were high power consumption sensors. So we are proposing a new technology based on anisotropic magnetoresistors that, well, are as shown. They are commercial sensors, as shown, of Honeywell, and they are designed in Whetstone bridge configuration, as shown on the top of the slide, on the right side. These Whetstone bridges has 4 magnetoresistive elements constituted by permalloy. That is a ferromagnetic material, an alloy of nickel and iron. These sensors that we choose has 2 axes. So they have a couple of Whetstone bridges, but they have a problem that is that they need a flipping noise reduction technique to recover from an external field, optimize the magnetic domains, and the extraction of the offset generated while sensing. The sensitivities of each sensor are shown here. That for the 1002 are 62 volts per Tesla, and for the series of 1022, 23 volts per Tesla. The 1002 has a greater sensitivity, but it consumes more than the 1022, and we decided to prove it, the 1022, to see if it fits with the requirements. Here's the working principle of AMR technology. The permalloy is, as I said, is an alloy of iron and nickel, and it's constituted by magnetic domain that are randomly orientated. But to ensure, to make the sensors reliable, we have to apply current pulses to magnetize these domains. And we said that magnetization through current pulses through electronic circuit. And we said that magnetization through the easy axis, the sensitive axis, is in perpendicular. And if we point, if an external magnetic field is on the direction of the sensitive axis, the resistance of these material will increase or decrease. Here's a die. Well, on the left side of the slide, I show a die. The sensors shown after have a couple of them, because as I said, they contain 2 axes. So in this die, we have the set reset strap and the Whetstone bridge elements. Here, if we see the electronic circuit as a black box, we can interpret it as the first row. as an input, we have digital signals that control the current pulses of the output. As shown above the slide, the circuit will be like that. We have a resistance on the EMR sensor that acts as a coil, as when they receive a current pulse, it generates a magnetic field that magnetizes the magnetic domains of the Wheatstone bridge elements. The power fed, well, the alimentation of the system is at 5 volts. The digital signals are set at 5 volts too, and the Wheatstone bridge, it's fed at 2 volts. Characteristics of the AMR 1002 is that it goes, the current peak is up to 2 amperes, and the 1022 is up to 0.5 amperes. These pulses doesn't take longer than 2 microseconds. I have to say additionally that the power consumption of each sensor, the 1002 and 1022, is below the 20 milliwatts, so we met the requirements on using both. Here I show the design of the 1022, the electronic circuit, well, the printed circuit board made for the AMR sensor 1022, and the PCB dimensions are the ones shown, and we design a prototype box, like model box, that will be made of aluminum, and is well, it has the shape that is shown here. The mass of this box won't be more than 100 grams. For the readout, the main contribution for the data acquired is from the sensor itself, but the readout doesn't have has a lower noise, and the readout of the magnetic sensors and the thermal sensor it's equal, because they are both resistive sensors, so they can be read on the same way. This stage is it's well explained, better explained at the poster of Jordan Morales, a colleague of the Institute of Space Science. Sorry, I didn't pass the slide. Well, here is the readout part, and as I said, the thermal sensors are rated the same way as the magnetic sensors, as they are based on the same technology. Well, here we have the setup of the magnetic sensors. The first image we can see is the mu metal chamber, that it isolates the sensor of external magnetic fields as the one of the Earth. And we use it to obtain runs down to the nanotesla root hertz. Well, to acquire data down to that magnitude. The temperature control chamber is to control the chamber where the temperature is controlled, so that is a controlled environment. And last of all, we see the Helmholtz coil that is used when calibrating the magnetic sensors, as it generates well, you insert a digital wave, well, a wave with a function generator, and it with the coils generates the magnetic field you want. Here are the latest results we achieved using both the 1002 and the 1022 AMR sensors. We go under, well, we achieved performances better than the requirements, as the requirements were set to 100 nanotesla root hertz, and we achieved less than 50 nanotesla. The conditions of at the time of sensing, of acquiring that data, was the sensors were placed inside the 3 layers of mu metal and inside the temperature control unit. And the whetstone bridges were fed at 2 volts, so the power dissipation was complies the requirements. As the conclusions, we can say that LISA needs a magnetic diagnostic subsystem to monitor the environment, as the test mass could be perturbed, and we have to detect that perturbances. The magnetic diagnostic subsystem we proposed is based on AMR sensors, and they meet the requirements set by the ISA. By implementing these sensors, we have achieved a substantial decrease in both power consumption and the volume of the magnetic diagnostic subsystem that, well, compared to LISA Pathfinder. And for further work, we should design the flight model PCB for the AMR sensors, as for the moment it's all commercial and is in a flight model version. And we need to study the back action effects of the AMRs to know how the distance we can approach to the test masses without disturbing it. And sorry, and that's all.
Thank you, Anna, for the interesting talk. Does anybody have any questions? If so, please, I encourage you to use the Q&A button down here. So far, I don't see any questions yet. Here's one coming up from an anonymous participant. So the person is asking, for magnetics within LISA, how many of these modules are required? Because I assume the magnetic field within the detector isn't just a uniform gradient.
For the moment are placed 6 for spacecraft, as they are 2-dimension sensors, and we need to know the 3 dimensions and around the spacecraft, so around the test masses. So for the moment are placed 6.
Okay. That sounds very reasonable. And if there are other questions, I would maybe encourage people to just post them, and we can answer them online, because then we can stay on schedule. So thanks again, Anna, and we can continue with Davide from the University of Trento on torsion balance testing of the continuous discharge strategy for LISA. So please, the floor is yours.
Thank you so much. So my name is Davide Bosco. I am a postdoc at the University of Trento, and today I will present our work our experimental work to measure the noise induced by the continuity strategy of the LISA test masses. So just to give an introduction, it is a well-known issue that isolated objects in space, such as the floating LISA test masses, get charged by cosmic rays and energetic particles coming from the sun. This is a problem for us because there is a force term which is directly proportional to the test mass charge. And it involves a coupling between the test mass charge and the residual stray voltage across the LISA sensor. So if the charge raises too much, we will not be able to see to reach the LISA sensitivity, but we will measure an extra noise which is related to the test mass charge. And so we'll reduce the performance of LISA potentially. Two noise sources are related to the test mass charge. One has to do with a non-zero test mass voltage that couples with some noisy stray voltages in the LISA sensor, which is expected to be the dominant term. And a second noisy term relates to the presence of a static DC stray voltage in the LISA sensor that couples with a noisy test mass charge because the arriving time of particle that charge up the test mass is at random. LISA Pathfinder both measure these, the charging rate and the noisy charging rate during the mission, and it uses a very simple solution to keep the test mass charge and this noisy term under control, the photoelectric effect. So the idea was to shine light either on the test mass or on electrode housing to produce a photocurrent with the photoelectric effect to counteract and keep the test mass charge under control. There are two possible discharge strategies that have been envisioned so far. One is the fast discharge, which was the default strategy for LISA Pathfinder, which entails just letting the charge, the environmental charge, accumulate on the test mass up to a given threshold, which was 70 millivolts, and then discharge with a strong illumination the test mass in a very short amount of time, of the order of minutes. During the discharge, the signal, the science signal was a little bit degraded because there were some transient and extra noise. So there was effectively an interruption on the quality of the data. In order to resolve this problem and to reduce any possible gaps in the science data or any possible degradation in the science data, a second strategy has been envisioned, which is a continuous discharge. And the idea is pretty simple, is to illuminate at all times the test mass with a suitable illumination pattern that keeps the test mass charge close to neutrality at all times. The problem is that the continuous discharge introduces an extra noise because the charge transfer between test mass and electrode housing is a stochastic process. It's as the charges are discretized and as the arrival photon is at random, it can be the charge transfer can be modeled as a form of shot noise. And so the charge itself on the test mass is the integral of a current, so it could be more or less modeled as a Poisson process. Moreover, as this procedure is still under testing, we don't know if the continuous discharge strategy may introduce other or unexpected noise sources on the test. So we need to test this strategy and make sure that it fulfills the very stringent LISA requirement. So what we tested actually? So we used so the new proposed UV LEDs, which are the new candidates sources for charge management of LISA, coupled with electronic unit to drive the LEDs provided by the group of INFN Roma. Why we used LEDs and not mercury lamps as in LISA Pathfinder? Because LEDs have several advantages. The most obvious one are that they are smaller, they weigh less, and they consume less power than UV lamps. they are still quite reliable. They have like a high dynamic range, so the power output, the light power output from the LEDs can vary by orders of magnitude. Instead, with a UV lamp, like the dynamic range was way smaller. And more importantly, the LEDs can produce very short pulses of light, which can synchronize with the electrostatic fields needed for the capacitive sensing of the depth position. For those who are into LISA with the injection voltage that are used by the capacitive sensing in the GRS. The possibility of synchronizing the illumination with these fields allows to fine-tune the equilibrium potential of the illumination by adjusting the duration of the pulses and the delay with respect to the zero crossing of the injection voltage. As you can see on the plot in the bottom right, by adjusting the delay, in this case of the illumination, we could achieve for both test mass and electrolyzing illumination a variation of the equilibrium voltage, which is more or less of the order of plus or minus 0.6 volt, which is related to the fluctuation of the test mass voltage induced by the injection electrodes. So with the illumination pattern, we can tune the illumination to reach potential equilibrium potential very, very close to neutrality without the need of adding extra DC fields around the. So this was the item under test, and we tested it with our torsion pendulum at the University of Trento, the 4 test mass torsion pendulum. You can see some pictures here. And finally, we used our torsion pendulum, which is a mechanical experiment, as an ultra-sensitive accelerometer, so an instrument to measure very, very small current. The characteristic of our setup is that it resembles very closely the geometry of the LISA gravitational reference system around it. So the electrode housing is basically a copy of the LISA pathfinder electrode housing. The test has coating as the LISA and the same geometry and the same feature. And the position of the fiber optic harness that brings the UV light into the GRS is the same as LISA Pathfinder. The only difference with respect to LISA Pathfinder is that we used, as I mentioned before, UV light from LEDs and not anymore from UV lights. But how can we measure the charge? Measuring on the test mass, the measure technique is quite simple. We modulate the potential on some of the electrodes of the pendulum, more precisely the X electrodes, which are along the sensitive axis. This induces a force on the pendulum, which is charge. As we move, yes. Okay, sorry, I don't know what it happened. My internet connection failed for a few minutes. Okay, so where I think on this view graph or on the next one, on the previous one? Okay, so I briefly recap what I was saying. So close to the equilibrium voltage, you can approximate the dynamics of our system as this equation here, which is just an exponential decay to equilibrium with a constant time constant tau, plus a noisy current, which is due to the stochastic nature of charge transfer. If we compute, go in the Fourier domain and compute the expected modeled power spectral density of the noise, we get to this to the third equation, in which on the bottom there is like a integrator response up to a given frequency, which is the inverse of the time. We assume for the noisy current power spectral density a shot noise form, which is proportional to a effective rate of charge arrivals, which is lambda effective. So to explain it in very simple words, if we start from potential and we turn off the illumination, there will be an exponential decay to the equilibrium voltage. We can measure the times constant of this exponential decay with a fit. And then once we settle to the equilibrium voltage, there will be some fluctuation around the equilibrium voltage, and this is related to the effect of this noisy current, which is in turn related to the fact that charge transfer is discrete and a stochastic process, and so can be modeled according to our model as a shot noise convoluted with a proper transfer function. First of all, we run some studies to see if we can actually see this signal, this noisy, which is not a signal, it's just a noise with our experimental setup. And the detection limits are quite tight. Moreover, there is a dependence on the UV power, because both these quantities, both the time constant depends on the UV power of the illumination, and also like the level of shot noise in the current depends on the power of the illumination. So the power of the illumination is a critical parameter and determines shape the spectral dependence of the noise that we are going to measure. So detection limit, because the noise is expected to overcome our sensitivity threshold of our setup only at very low frequency. So more or less the model, but here I will explain how we carry on. So the measurement idea is quite simple. Okay, so the conclusions.
Yes, please, that would be great, just for the sake of time.
Okay, so yeah, so, sorry, excuse me, I don't know, it's like a technical problem I never experienced so far. So the idea, so we acquired several time series, we computed the spectrum, we compare it with our model, depending on the UV power. And then we try to fit the data with our model and extract information about the effective rate during illumination, and how this depends on the other parameter of our model, which is the response time tau. And so here in the bottom, you can see the model, and you can see in our model, the effective rate of the noise depends, is inversely proportional to the measure response time of the system tau. So we fit our data with this power dependence, and the result is that more or less the dependence is what expected. So this exponent b is quite close to -1. It's a little bit smaller. It's a little bit different from -1, so it's around 0.9, probably because in the measurement with the very low power, there is the background of the torsion pendulum starts to kick in, and so we measure more noise than expected. But still reducing the power as much as possible, we can obtain an effective rate which is below the current requirement for the noise, effective rate of the charge noise for discontinuous discharge for the dissolution. So we demonstrated that with our torsion pendulum, with a suitable setup, illumination pattern, we can achieve during continuous charge a charge noise which is below what is required for LISA at this time. So this is like an experimental confirmation that the continuous discharge strategy can work, and it induces a noise which can be kept within the LISA requirement. So that is the main takeaway of my presentation. Again, sorry again for the instability of my internet connection, but if the people are interested, I'm available to answer some questions, or online or offline.
Yeah, thank you, David. So it was indeed a very interesting presentation, and those are really promising results, but I would encourage people just to post the questions so that we can proceed with the next speaker now, because we are a little over time. Yeah. So Yeah, thanks again.
Okay.
The next speaker is Federico Sabatini, and he's from the University of Urbino, from Italy also, and yeah,
hello.
Please.
I share my screen.
Not yet, please share it. Can you do that? Or I'll see what I can do. Ah, yes, there it comes up. Perfect.
Okay. Good morning. I am Federico Sabatini from the University of Urbino in Italy, and I am an IT PhD student, and I collaborate with the LISA group. In particular, I develop machine learning models for the future LISA mission, taking into account the lessons learned with the precursor mission LISA Pathfinder. From the point of view of the interplanetary medium impact on future space interferometers for gravitational wave detection, it is very important to take into account the presence of nearby spacecraft that may provide precious data about the interplanetary medium. And it is also important to consider the possibilities that we will have to trace the solar activity nearby the space interferometers. I quickly recall that the three LISA spacecraft will be orbiting trailing Earth at about 50 million kilometers. And at the time of the precursor mission LISA Pathfinder that orbited around L1, there were other missions for the interplanetary medium monitoring around L1 that were ACE and WIND, but at the time of LISA, there won't be any nearby missions for this purpose, because we will have probably the European Space Agency mission Vigil orbiting around L5 and dedicated to space weather. And around L2, we will have the AMS 100 mission for galactic cosmic ray measurements. Here I have reported Monte Carlo simulations for the LISA spacecraft, and in particular here I have shown the gravitational reference sensors, the two green cylinders, hosting the test masses that play the role of the mirrors of the interferometers. And in LISA, the distance between the mirrors will be of 2.5 million kilometers, and in LISA Pathfinder, this distance was squeezed to 30 centimeters. The LISA Pathfinder test masses were the same that will be placed on board LISA, and were gold platinum cubes of about 2 kilograms. LISA Pathfinder orbit was flying in L1, and it was basically observing fluctuations of the interplanetary parameters that are solar wind speed and interplanetary magnetic field intensity variations, very similar to those gated at the Earth. LISA Pathfinder also hosted a particle detector measuring the galactic cosmic ray variations above 70 milli per nucleon. And it is possible to notice here in the left figure that during the Gold LISA Pathfinder mission, the galactic cosmic ray flux was increasing because the mission orbited during a period of decreasing solar activity. In the same figure, it is also possible to notice all these fluctuations that are associated with the transit of high-speed solar wind streams, for example, these galactic cosmic ray variations highlighted in blue, or the transit of the interplanetary counterparts of coronal mass ejections, as for example, this galactic cosmic ray variation highlighted in red. The transit of these structures modulated the galactic cosmic ray flux as a function of the energy, and these processes must be studied because the test masses are charged differently by galactic cosmic rays and solar energetic particles, much more in this latter case. Here I want to stress the role of the interplanetary counterparts of coronal mass ejections in modulating the galactic cosmic rays and the effect on the test mass charging. As an example, I reported this event observed with the Pamela experiment in December 2006. we have reconstructed the whole dynamics of the event, and we observed that in only a few hours, the galactic cosmic ray flux decreased by a factor of 2. The estimated variation on the test mass charging decreased by a factor of 4, and the noise associated with the same event by a factor of 3. About the effects of these kind of events on the LISA sensitivity, see the next talk by Valerio Ferroni. By the way, to study the effects of the noise on LISA, we have to control the transit of interplanetary structures. The problem is that on board LISA, we will have magnetometers placed inside the spacecraft that are not aimed at monitoring the variations of the interplanetary magnetic field. Anyway, there is the possibility to reconstruct the variations of the magnetic field within an accuracy of 2 nanotesla. And on this, I recall that the intrinsic fluctuations of the interplanetary magnetic field are about half nanotesla. And the second problem is that on board LISA, we will not have any information about the solar wind speed, and we will not have nearby spacecraft for this. So we will not have information about the solar wind speed that is the only real fingerprint for the passage of high-speed solar wind streams that modulates the galactic cosmic rays. For this reason, I developed 2 machine learning models that are able to reproduce the solar wind speed based on galactic cosmic ray observations that will be also available on board LISA. I described first the machine learning ensemble model. Here I reported the workflow of the model, the training phase above the red line and the prediction phase below the red line. For the training phase are required the LISA Pathfinder galactic cosmic ray data and the ACE solar wind speed data. Time series are hourly binned and time aligned and then pre-processed in order to obtain these 4 datasets. Then each one of the dataset is provided as input to each one of these weak models that are a linear regressor, a KNN, a support vector machine, a random forest, and 3 neural networks. So we have an overall amount of 28 weak regressors that provide as many weak predictions. To obtain the ensemble model prediction, we require the LISA Pathfinder galactic cosmic ray data that are processed as the training data in order to obtain the 4 datasets that are provided as input to the weak models, and the weak predictions are averaged in order to obtain the ensemble model prediction. Here I reported the differences between the 4 datasets that are in the moving average used to smooth the data, that may be 3 or 5 hours, in the time lag between galactic cosmic ray observations required to obtain the predictions, that may be 1 observation every 3 or 5 hours. In the number of the galactic cosmic ray observations preceding the instant to be predicted that are required, that may be 24 or 48. And as a consequence, we have preceding time window of galactic cosmic ray observations that may be of 3, 5, 6, or 10 days. Because, for example, if we have 48 observations of galactic cosmic rays, 1 every 3 hours, we have a time window of 6 days. As for the training test splitting, we have the LISA Pathfinder data during 18 Barta rotations, sun rotation. So we use 15 rotations as a training set, 2 rotations as the validation set, and the remaining 1 as a test set. Here I reported an example of a dataset, the dataset 4, to predict this solar wind speed data point. For example, we need to smooth the time series with a 5-hour moving average. And then we select this 10-day time window preceding the instant to be predicted. And inside this time window, we select the galactic cosmic ray observation at the same instant of the output, and 48 preceding observations, 1 every 5 hours. So we have 49 input features and 1 output variable. This model, this ensemble model, is based on an heterogeneous pool of opaque weak regressors, and it is able to provide predictions with a mean absolute error of about 67 kilometers per second. I take this chance to highlight that the solar wind has an intrinsic fluctuation of about 10 kilometers per second, and at high speed. And the measurement of ACE has an uncertainty of about 10%. So by combining the two errors, we have about the 14–15% of error. And this model requires huge amount of input features, even if they are only about galactic cosmic ray observations. And for this reason, the model lacks of human interpretability. And given the huge amount of input features, it is not possible to apply symbolic knowledge extraction techniques in order to obtain predictions that are human interpretable. So I developed a new machine learning model, this time based on a single KNN regressor. I perform feature pruning in order to obtain a limited amount of input features. And this time I also select the features of the interplanetary magnetic field intensity. The model is still not human interpretable, but it has comparable predictive performance with a mean absolute error of about 64 kilometers per second. And given the limited amount of input features, it is possible to apply knowledge extraction techniques and obtaining satisfying results. So I applied the creepy extractor, and I obtained interpretable predictions that have a mean absolute error absolutely comparable with those of the KNN and the ensemble model. Here I reported the workflow of this second model. So we have the LISA Pathfinder galactic cosmic ray data and the ACE solar wind speed, and also interplanetary magnetic field intensity data. Time series are hourly bin and time aligned. Then I create the data set, I perform a feature pruning, and then I split the data set between validation set to perform a model selection, training set to train the model, and test set to evaluate the model. After having trained the model, I can obtain opaque predictions, or I can apply symbolic knowledge extraction techniques in order to obtain human interpretable predictions. Here I reported the input data required by the second model. So to predict this solar wind speed data point, we need preceding 9-day time window for the galactic cosmic rays. And within this time window, I select the slope of the galactic cosmic rays during the whole time window, and the slope during the last 2.5 days. So we have two features for the galactic cosmic rays, and other two features for the interplanetary magnetic field intensity. These features are selected inside the 3-day preceding time window, and are the maximum value and the minimum value of the magnetic field intensity. So we have 4 input features instead of 50 or more. After having trained the model, I applied the symbolic knowledge extraction techniques named Creepy. Creepy provides human interpretable rules that are propositional rules in the form of if, then, else. The if part of the rule describe hypercubic subregion of the input feature space, described in terms of interval inclusion of the input variables. So in this specific case, I obtained these rules for my model, and the rule is if the minimum value in nanotesla of the interplanetary magnetic field intensity is within this interval and the maximum value is within this other interval, and if the slope of the galactic cosmic rays 9 days before is inside this interval, and the slope 2 days before is inside this other interval, then I can obtain the solar wind speed by applying this linear combination of the input variables. Otherwise, I can apply this other linear combination. It is interesting to notice that from this linear combination, it is evident how the solar wind speed is proportional to the magnetic field intensity and inversely proportional to the galactic cosmic ray flux slope. So here I show you the results of these models. On the left, we have the predictions of the ensemble model in red, and I also added these red shaded regions to show the uncertainty of the predictions calculated as the standard deviation over the weak model predictions. And here on the right, I reported the KNN predictions in red, and the output obtained with two symbolic knowledge extraction techniques that are CART and creepy. CART, you can see it in blue. You can see that it is not very accurate in all cases because it introduces an undesired discretization in the output values. Conversely, creepy is much more in agreement with both the data and the KNN predictions because it provides a linear combination of the input variables as input, so it may be more accurate. So in conclusion, I presented two machine learning models that are able to reconstruct the solar wind speed with an average error of about 70 km per second. That is the 10% with respect to the maximum value of the solar wind speed observed during the whole LISA Pathfinder mission. Only galactic cosmic ray observations or galactic cosmic ray and magnetic field observations are required as inputs for these models. And with the second model, it is also possible to obtain human interpretable predictions. Both models may provide estimates for the future LISA mission, and in the future we want to perform a fine-tuning of the interpretable models because we want to achieve better results in presence of galactic cosmic ray non-recurring variations. And for me, it's basically all. Thank you very much for your attention.
Thank you very much, Federico. Are there any questions? Please feel free to use the Q&A. Or just unmute yourself and speak up if you want to. So far, I don't see any questions. Yeah, if there are none, I might have a really simple one. Like at the very beginning, on your, I think, slide number 4, you showed a plot where the count was actually, yes, this one on the top left here, where this count was increasing.
Yes.
And you have a decreasing solar modulation. So can you say a bit more about this solar modulation? So why is it that your count rate then goes up if that modulation goes down?
Yes, of course, I'm not a physicist, but I am a computer scientist, so it is not my my field. But
sorry.
LISA Pathfinder was flying during a period of decreasing solar activity, so there were as the solar activity decreased, there are more particles reaching the spacecraft, the particle detector on board the spacecraft. So we have this this increase in the count rate, basically.
Oh, thank you. Maybe I need to read again the papers over the summer. Yeah. Okay. Yes. So then. If there are no other questions, then thank you again. And we will proceed with the next and last speaker of our session, Valerio Ferroni from the University of Trento.
Thank you, Sarah. So I can grab the screen and present. So in this presentation, I'll discuss with you some of the first results of a toolkit that we developed under the framework of a ESA contract that handles the effect on the environment on LISA. In particular, the charging I called signals because with the solar activity and time frame where LISA will fly in, the solar modulation will change, and some effects from the solar activity and other features will create charging that is not stationary, but change over time, and then has even transient effects that could be interesting to study for LISA, in particular for its noise budget, but also for data analysis. In this work was done with the old within the old Unity N group workforce, but with our young old star Martina and Leonora that left a year ago almost, and there is a strong collaboration in this work with the University of Urbino and the Urbino group. So briefly, so in the cellular environment where LISA will fly in, we have, as Federico mentioned just before, galactic cosmic ray and solar energetic particles seldom that will hit the spacecraft, and then creates from primaries that are almost protons, but also in a few parts nuclei and electrons, other particles. We create showers of particles that eventually will charge up the test masses of LISA, which are a reference point for gravitational wave measurements. And because they are isolated and mechanically and free floating, though, they will charge up. And this charging up, you know, if you have something that is charged and there are electric fields around, a force arise that creates force noise if the charging is not stationary, as Davide mentioned before, or if the stray fields are not stationary. So we had in our tradition this delta X as an indicator of the stray fields, which is actually equivalent potential difference across X electrodes. But you can imagine electric fields led by this delta X that creates a force on a charged test mass. So the test mass must be neutral or close to neutral in order to suppress this force source, and stray fields compensated in order to keep both this noise force term small enough. But you know, you have a force which is Q times E, which is the electric field. If apart from the noise, if the charge changes, you have a force change. You have somehow a charge signal that induces a force. So how about that? So to tackle all these problems, we developed a toolkit which is able to take care of the interaction of the primary particles on the spacecraft, and calculate how much the test mass will charging, and not only this, we also this toolkit will be able to consider handles different solar modulation conditions, so different fluxes, handles solar events, so SEP, which are solar energetic particles, so Forbush decrease, so short transient in the galactic cosmic ray flux that lasts a few hours within a day or two. And we will identify contribution of different particles at different energies and calculate not only the charging of the test mass also, but if we have some of a charging signal induced force, how about these signals in terms of SNR? So if you're not considering the noise term, we will see something like a signal popping up in the LISA science data. How will we tackle this? How will we consider this? Will be considered as a gravitational one, if that could be considered as a gravitational one if we are not able to distinguish that from a charge one. So the framework of the of this toolkit is quite simple. So we have a simulation part, which is mostly a Monte Carlo simulation, and then we have an analyzer that and a sensitivity analysis, as we called it, that is able to take the output of the Monte Carlo simulation that gives us the particle hitting the test mass, so the charge deposit that reach the test mass, and creates with the electric model and some simulation, some statistical analysis, calculates the force term and the SNR for LISA. The geometry in this moment it's quite simple, but still is representative as is typical in this Monte Carlo simulation for the charging. So we don't have the spacecraft, of course, on hands. So we use this simple geometry with spherical shells that simulate somehow or model the amount of material surrounding the test mass. And we have these test masses surrounded by this cubic shell that simulates the last part, the last surrounding of the test mass. So with our toolkit, so we take out the Monte Carlo simulation that gives us the deposit of the charge on the test mass. We will obtain something like a time series, like on the one on the bottom left. So over time, you see how much charge is deposited on the test mass. You would see numbers that goes from -10, -12, up to 20. So that means that at some instant you have 20 charges deposited on the test mass. And that is calculated with the Monte Carlo simulation. And you see here on the top the histogram of the deposit. So how much is the deposit, how much is the rate that we are expecting to, we are simulating, so we are calculating for the test mass. So we have a toolkit, we can somehow simulate a charge measurement on the test mass. So you will see on the right a charge ramping up because of this charge deposit. And because this is a not stationary process, the charge is not is as a stochastic nature. So we have a noise figure. So which is basically the charging is something like a shot event, shot noise event. So the charging. So the charge accumulator, it is an integral of the charging. It's has this shape of 1/f in frequency. And so with the stationary flux, we can calculate, we can simulate a charge measurement. So we can have, we can see how the charge will evolve on the test mass. But more importantly, just connecting with the work with Federico, if you have a charge event like a SEP or a Forbush, you can from our Monte Carlo, we have a charge deposit in different condition of the flux, and we can simulate we can build an event like a SEP here on the right, combining different output of the Monte Carlo. You will see that charge here goes from 0, and then with the solar event reach a stationary value here after typically scales of half a day or a day. And so if we consider this charge signal here, we combine that with the electric field of, coming from the stray fields, and we do some SNR analysis. So we calculate how this signal will pop up on the LISA band. We calculate the signal to noise frequency. And see how this signal will be important. For this part, I will give you a couple of examples. So considering the Pamela data in 2006, we have in December a Forbush decrease just after a SEP event, considering this Forbush decrease, you would see on the left the charging that is steady, and then as a quick drop in a few hours, and then recovers up at the previous level after a day or so. This kind of a depression of the charging pop up as a transient signal. You will see here how the force is as a linear trend, and then as a quick flattening, and then a recovering. And then if you consider this signal and the LISA sensitivity, just considering as just one Tesla for simplicity. So it's a Michelson interferometer, so a TDI X combination with just one Tesla. You can consider at the most a factor of 2 of this as an underestimation. You would see that the SNR is quite small, 0.1, but it's dependent on the delta X on the stray fields. That here we assumed as a 5 millivolts, so as a compensated field. If we consider then a SEP event, just the one that happens before the Forbush event that I just presented, here we see that you have a strong, in this case, a strong charging up in something like 10,000 seconds. The charge that typically with the galactic cosmic rays, it's around 20, 30, 40 charge per second, rise up to 2,800 charge per second very quickly. And because the force is proportional to the charging and the delta X, you would see that you have a strong signal, which is something like a step force event lasting a few hours. And the SNR in this case, even with a compensated stray field, it's quite interesting. It's around 20. You see on the right, I forgot about that, to construct these fluxes from Pamela, we had to use not only the data from Pamela, but use our model that was developed in particular by Urbino Group in order to calculate the flux at the different phases of the events. And that was done by Catia and its group. And you see on the right the flux reconstructed by her model at the different condition of the SEP. So at the onset, then at the mid phase, and then at in the deep part, that correspond to the peak of the charging, the middle part, and the decrease here at the end. So to summarize somehow what I discussed, so we have this framework that allow us to simulate and analysis the charge events in LISA. We calculated SNR for in this case just for X combination TDI, but just for one Tesla, so we are quite underestimating the effect. The SNR that we found was marginally important for LISA Forbush, but if the stray fields are not compensated. But for a SEP event like the Pamela one in 2006, that could be important. The effect, as I said, is underestimated because we are considering in this moment one Tesla. But depending on the TDI combination, more Teslas, of course, are involved than one. This Pamela, just to give you an idea, these Pamela events can happen around up to 10 in 1 year of LISA. In particular, in the maximum solar flux, maximum solar activity. But because LISA will fly around 10 years, I hope, so the solar activity will change and invert completely. So we would see a complete phase of solar activity that goes from a maximum to minimum. and I come back to maximum. So this rate of up to 10 of this Seppia and Forbush events would be visible only for a few years in LISA. And this is LISA, of course. And one thing that is still have to add is the charge management response. So we assume at this moment that the charge management is not playing any role in counteracting these charge events, but this has to be included in this analysis. But in general, I think for us, I think it's interesting to consider this charge signal for simulation and for CMS operations. So to study what would be the possible counteracting measure that we could use with the CMS, the charge management system, in order to suppress this charge signal. But in general, also to help data analysis in order to veto some strange signal visible in LISA if they are coming from charge events. Just to mention, with the coupling this toolkit, this toolkit with the FEM model, we were able also to consider other different effects for LISA, in particular the effect on the fields and the stray fields on the charging of from the environment over time. That would also be interesting. If you want, you can ask me about that. So I think I'm done. Thanks.
Well, thank you, Valerio. Are there any questions? So yeah, again, please either unmute yourself or use the Q&A as you wish. So while people are thinking about possible questions, so again, maybe I just take the opportunity and ask one. So with your toolkit, would it be reasonable, or are you thinking about including this into some of the LISA end-to-end simulation activities, for example?
Yes, of course. So I'll be say on touch is quite not honest, but with the simulation working group, I'm planning to present this work, and then somehow I will try to merge this part and the result of this work in the simulation code and simulation for LISA. See, I think it's you're right. This could be interesting, of course.
Yes, of course. Yeah. So looking forward to that integration. So well, so far nobody has posted anything. So please don't be shy. We certainly have time for one more question. Yes. So if there are no questions for Valerio, maybe Bill, you have one.
No, I was just going to comment that you have it's a shy crowd this morning. So
yes, maybe also just in the process of digesting all the information, because yeah, it were very interesting and very dense talks. So thanks again, Valerio. And well, really there are no questions or anything else people would like to discuss, then I would like to thank all the speakers again for that session. If questions are popping up, then don't hesitate to contact anybody via email or in this Oxford Abstract platform. There's also the opportunity to leave comments on all the talks. And well, then, yes, I would like to thank everybody who has presented today, and also everybody who took the time and actually tuned in. And well, the meeting continues this afternoon at 4 in the European summertime with some interesting plenary talks. So thank you very much, and goodbye from my side. Well, it's 11 o'clock here, so good morning or good afternoon, whatever fits your time zone. Welcome to this session on constraints on modified gravity. My name is Sarah Paskowski and I'm from the AI in Hanover. And I would like to welcome our first speaker here, Iris van Gemeren from Utrecht University in the Netherlands. Please, Iris, the floor is yours.
Thank you, Sarah. Let me share my screen again. And I want to put it in presenter mode. Can you see my screen?
Yes.
Perfect. Then I'll start. Okay, so welcome everybody to this talk on black holes letting their hair down. My name is Iris van Gemeren. I'm a first year PhD student at Utrecht University. And before I start, I would like to thank Banafsha Shivalilu, as she did a lot of work on this study, and also my two supervisors, Tanja Hinder and Stefano van Doren. And of course, also the organizers for the opportunity to let me present this talk. So the topic of this talk will be on probing scalar hair environments around black holes in scalar Gauss-Bonnet gravity. And we do this by studying scalar tidal effects and also then analyzing the imprint on the gravitational wave signature. So to start, I will tell us a bit about the modified gravity context of this story. So to start, one of the main open questions in theoretical physics is, of course, what is the true nature of gravity? And to answer this, there are a lot of extensions on top of general relativity, our current gravitational model, to extend this theory and see if it would describe maybe gravity better than GR itself. And in this talk, we've kind of taken phenomenological point of view to this by saying we take one such modified gravity models and see what it will do to our gravitational wave signature and how this would change with respect to GR. Therefore, we specify to a promising gravitational theory called scalar Gauss-Bonnet gravity. And to actually analyze what are the differences with GR, I put here the action on the slide in the box. So one can see that the first term of this action is our normal Hilbert-Einstein action. And on top of this, we add a scalar field. And the scalar field phi is coupled to a quadratic term in the curvature. And this quadratic term, in the case of scalar Gauss-Bonnet gravity, is given by the Gauss-Bonnet invariant, which is given here below. The coupling to the scalar field happens via a coupling constant alpha. This one needs to be constrained via observations, and also a coupling function f, which is here kept generic, but you have different choices for this coupling function, also leading to different versions of this scalar Gauss-Bonnet models. And there could also be a kind of potential term, which might add an additional mass to the scalar field or interaction terms. This theory is in general considered promising, as in general adding a quadratic term in the curvature makes the theory renormalizable, which is one of the problems with general relativity, but also does not introduce any mathematical instabilities in your field equation, so that's also very nice. There are also motivations coming from quantum gravity paradigms. However, generally in these kind of setups, one considers this action as an effective description of gravity, so kind of a higher order curvature extension of GR, and therefore this action would be your fundamental action to work with. One of the interesting things about this scalar Gauss-Bonnet gravity is that when you look at your black hole solutions coming from your field equations from this action I just showed, the black hole solutions are actually different from general relativity. And in scalar Gauss-Bonnet gravity, we can also evade the no-hair theorem. So we can have black holes with a scalar field environment around them. And the scalar field environment can arise in different ways. So this depends on your choice for this coupling function f. So for example, you can choose a quadratic coupling function. And in this case, the arising of the scalar field can happen in a spontaneous way. This is called spontaneous scalarization. After a certain threshold value is crossed, then the scalar field arises. So then the black hole solution changes from your GR black hole solution as Schwarzschild or Kerr to scalar field configuration around the black hole. Another choice of coupling function would lead to a scalar field environment that is non-vanishing, that's just always there. And one of such choices for a coupling function is an exponential coupling. Then the scalar Gauss-Bonnet gravity relates to Einstein-Dilaton Gauss-Bonnet gravity. And this is also the case we consider here in this talk. Also, the properties of these scalar Hare environments are not like an independent new charge that's introduced. It is depending on the parameters of the system, of the theory, sorry. For example, as the figure I put here on the slide below, there we compare a scalar field surroundings without any scalar field mass and introducing a small scalar field mass and see what are the differences. And one finds that for a massless scalar field, the scalar field configuration around the black hole, the scalar cloud, kind of falls off in a 1/r distribution to infinity. But introducing a small scalar field mass confines the cloud more to the black hole itself, and also the fall off of the field is steeper, it becomes an exponential function. And these dependencies on the theory also comes around in the fact that from a regularity constraint of the scalar field on the black hole horizon, this gives a constraint which relates the scalar field on the horizon also to the horizon radius, and in the case of having a scalar field mass, also to this mass. So it's not an independent field, it really couples back to the parameters of the theory itself. And on itself, these environments are very interesting to study, but to relate it to gravitational waves, you need to consider a binary system with two black holes with these environments around them. And we actually take the next step here by considering leading order interaction effects of these clouds. And here we focus again on massless scalar field clouds, so not with the scalar field mass, but massless. The tidal field in this case, to characterize these interaction effects, we look at scalar tidal effects. And the tidal field, in this case, the tidal field E, is given by the gradient in the scalar field around the black hole. And the tidal field deforms the scalar field of the other body, of the other black hole in the binary, by inducing a dipole moment, Q. And to characterize these tidal effects, one normally introduces tidal deformability parameter, lambda, which is given by the ratio of this induced dipole moment Q over the tidal field E. And in scalar Gauss-Bonnet gravity, for the first time, we calculated what this tidal deformability parameter is. So we found that it scales linearly with the mass of the black hole, the coupling constant, and the second order derivative of the coupling function. So in general, we were interested in coupling functions with non-vanishing second order derivative, and therefore we focused on this exponential choice for the coupling function. To make then the connection to gravitational waves, we focused on the in-spiral modeling of a black hole binary. And we have now some differences with respect to general relativity, because we have corrections coming from the higher curvature terms we added to the action, but we also have now scalar radiation because of the additional scalar fields. And then we also introduced these interaction effects via these scalar tidal effects, which leads to a change in the energetics of the system of the two bodies. So the dynamics is changed, but also additional radiative energy loss. And to calculate the waveforms of such an in-spiral from one coalescing event, one can exploit the hierarchy of the different scales in the problem by matching different approximation schemes. So near the sources, to model the dynamics, one can do a post-Newtonian approximation, and to actually calculate the asymptotic radiation, this is matched to a multipolar post-Minkowskian expansion. And here we built on top of previous work done on already calculating this in scalar Gauss-Bonnet gravity up to 1 order in the post-Newtonian expansion. And we revised this to see how these tidal corrections would come into this description. These tidal terms are actually added as kind of finite size corrections to the skeletonized point particle description, meaning that during the in-spiral, as the separation between the two bodies is large, one can effectively describe the black holes as point particles moving along their corresponding world line. And all the corrections coming in from the fact that you're actually dealing with extended objects, and so also a scalar field cloud around the black holes, are kind of small corrections to this description. So the tidal terms are also added in this way. To do the actual analysis, we focused on the phase evolution of the gravitational waves, as this is kind of the main interest for data analysis. And that this was an interesting thing to study was already clear from this previous study, which I also show here a plot on the bottom of the slide, where in the right figure you can already see phase shift happening between the blue curve, which is the Gauss-Bonnet case, versus the black curve, which is the general relativity case. So from our analysis, we mostly compared to the total phase evolution, the tidal contributions versus the higher curvature contributions related to the Gauss-Bonnet terms, and the dependencies on the properties of the system. So I summarize here a few of our main findings. So we compared the very early in spiral phase evolution, where the bodies are very large, but still have a large separation, versus the later in spiral, and then the difference between these tidal versus the higher curvature contributions. And we found that actually during this very early in spiral, the magnitude of these tidal contributions was larger than the higher curvature contributions, even though they come in the same order in these approximation schemes. Well, during the later in spiral, when the bodies come closer together, the higher curvature terms become more important as the curvature becomes more important, where the bodies come close together. And we actually found then that the magnitude of these contributions becomes larger than the tidal contributions. However, these two contributions in the total phase expression come with opposite sign, meaning that the enlarged differences with respect to general relativity, because of these higher curvature contributions, are partly cancelled by the addition of these tidal terms. Furthermore, one of the interesting things was in the Fourier domain, in the phase of in the Fourier domain, we found the dependency of the tidal contributions on the coupling constant alpha, namely that for a smaller value of the coupling, we find larger tidal contributions to the phase, while you would expect the opposite for dependency on the coupling constant. However, after further analysis, we found that this is actually due to the fact that you're in the Fourier domain and not in the time domain, because in the time domain, this relation is flipped. However, as for data analysis, the Fourier domain is the most interesting part to study. This could still be an interesting property. And this also actually works true in the total phase evolution. So that's what's in the plots here below. So here I plot the total phase evolution in the scalar Gauss-Bonnet case versus with the difference with the general relativity phase evolution for a certain choice of a black hole system. And here we need to find that for the total phase evolution for a smaller value of the coupling, which is the green curve, the difference with general relativity is larger than for a larger value of the coupling, which is the black curve. Well, this relation is the opposite during the later part of the in-spiral. So this different dependency on the coupling constant, but we not only found this for the coupling constant, but for example, also the dependency on the mass ratio between the two black holes. That is also different from the early in-spiral to the late in-spiral. This might give interesting opportunities for multiband detection. So to give a crude estimate, we made the following figure, where we show one of the systems we considered, so a 30 solar mass total solar mass black hole system. And this vertical line denotes on the left side this early in-spiral part of the in-spiral, and on the right side the later part. And we also plot then the LISA sensitivity curve and the Advanced LIGO and Einstein telescope ground-based detector sensitivity curves. And we saw that this early in-spiral part lies partly in the LISA band and the later in-spiral part in the ground-based detector band. And being able to detect it with both of these different frequency regimes with both detectors might give the possibility to mitigate some of the degeneracies between these tidal contributions and the higher curvature contributions, which might give an interesting opportunity as we have these different scalings with the coupling and also, for example, the mass ratio. So as a take-home message, we saw that in scalar Gauss-Bonnet gravity, the black holes have very interesting other solutions with respect to general relativity, and also these interesting scalar configurations around black holes, which on itself is already very interesting to study. However, to actually probe these environments, gravitational waves are a very interesting tool, and therefore we compared to the gravitational wave signature during the in-spiral, these higher curvature contributions and these scalar tidal corrections. And among others, we found this interesting dependency on the coupling function in the frequency domain, which might lead to interesting opportunities for multiband detection. And as an outlook, one could extend maybe this analysis to a massive scalar field, not only considering a massless scalar field, and also include other tidal effects. So now we only looked at purely scalar tidal effects, but one could also include mixed tidal effects or gravitational tidal effects. And there's now probably also a bias on the parameter estimation of this coupling function alpha, as these tidal corrections were not taken into account yet in these parameter estimations, which might lead to other constraints on the coupling constant. So with this talk, I hope I sparked your interest. And if you're interested, I also put like the QR code of our paper on the slide. You can scan. I will leave it on when we answer questions. And for now, thank you for your attention. I'm happy to answer any questions.
Yes, thank you for this very concise talk. Are there any questions? So you can answer, you can ask questions via the Q&A function, or you can just also unmute yourself in this session and ask your question or raise a hand. Any way will do. Yes, there is a question from Sebastian, please.
Hey, Iris, can you hear me?
Yes, I can hear you.
Okay, very nice. I have a question regarding on this last point on the bias. You showed that introducing this effect, you get differences with respect to GR for the same parameters, I guess. Have you also looked whether you can basically get similar behaviors by changing the parameters of the system, but assuming it is general relativity?
If you can get similar phase shift, you mean?
Yeah.
Or changing other parameters. So that's a good question. I guess in principle, you can also get a phase shift if you change other parameters of the system. However, we look at this phase evolution, so per frequency or in the time domain, the time evolution, and that is often very specific to the kind of change you make. So I expect that it's different in time related to what you're changing. So I would expect that these tidal effects give a different evolution than changing another parameter. But it would be a good thing to explicitly check as well. Yes, we didn't do this explicitly. Yeah.
Okay, thanks.
So I don't see any other questions at the moment. So we still have some time, so you can make use of that. And in the meantime, while people are thinking about more questions, so maybe I'll use the opportunity and ask one. So since I work on LISA, I'm obviously very interested in that sensitivity plot that you showed, and I was wondering if you can say how this changes for different mass ratios, like this pink curve.
Yes, so we did indeed plot also this for different mass ratios, and I think the change was not so large. Let me think what we found here. I think we had mostly shifted the curves like slightly up and down for these different mass ratio systems, but we did not like study extreme mass ratio systems, only like stellar black hole masses and also the mass ratios related to this. So we had kind of a slight change up and down, but it lied mostly still in the LISA sensitivity curve band.
Yeah, that looks promising. I mean, there is some margin here, right? So
yeah, exactly. So we did study this slightly, but not almost move to the extreme mass ratio case, which might be for LISA more interesting, but yeah.
Yeah, thank you. Any other questions?
I think I can also like later answer questions in the Q&A option, right? I think.
Yes, of course. And also on the Oxford Abstracts website, you can always post comments to different talks. So yeah, that's also an opportunity if the questions pop up later.
Okay. Yeah.
Yes, with that, thanks again for the nice talk and the answers. And then we can proceed with our next speaker, Sebastian Völkel from the Max Planck Institute for Gravitational Physics, or AI, in Potsdam in Germany. Please take it away.
Okay, thank you very much. Can you see my screen?
Yes.
Okay, great. So yeah, first, thanks of all, Sarah and Holly, for chairing it, the session. So I will talk about how we can constrain modifications of black hole perturbation potentials near the light ring with quasi-normal modes. And that sounds very technical, but I'll try to give the main message in a fairly simple way. And this is work in collaboration with Nicola Franchini, who's now in Paris, Enrico Barauza at CISA in Trieste, and Emanuele Berti at Johns Hopkins, and the talk is based on the paper that you can see here. So what's the motivation? So black hole quasi-normal modes, we had different talks already in this conference here, are a central piece of what is called black hole spectroscopy. So when you excite a black hole, we know it is stable, it settles down to equilibrium, and it emits gravitational waves with characteristic frequencies and damping times. And this allows us, in principle, to test the hypothesis that go into the no-hair theorem, which basically says that astrophysical black holes should be described by the Kerr metric. And of course, this also means testing general relativity. So this is interesting because with the ongoing measurements of LIGO, Virgo, Kagra, we can observe gravitational waves from black holes that merge, and in the future with more and more precision. So we are very optimistic that we can measure quasi-normal modes, and for some of the systems we have found the fundamental mode. There are some claims that also one overtone might have been found, but for sure in the future we will have much more data on that. And the nice thing about this is that it's in principle a clean test. So if you compare this, for instance, with the image of supermassive black holes, in that case, you need to model the accretion disk. So you need to understand what the matter is doing around the black hole to describe everything that leads to the final image. So that's really cool. But in that language here, I wouldn't call this as clean as just a vacuum black hole that rings down. But also that case is not so trivial as it might seem. And especially in recent years, this field became more multidisciplinary, I would say, because while in the past we mostly used perturbation theory, now we also have numerical relativity to probe the nonlinear aspect of the ring down, and of course data analysis tools to extract it from simulations or from data. So there's been a lot of work, in particular in recent years, on some of these nonlinear aspects, on systematic aspects. So we had, for instance, yesterday a talk by Pierre Moria about overtone fitting. We have a talk just after mine in a parallel session by Peter James Nee about similar aspects. So especially in recent years, people have tried to robustly extract quasi-normal mode overtones from simulations or from data. And there are several problems that people have found. And I just list some of them. I will not go into detail of them, but for instance, you can have nonlinear mode effects. So you can have modes that couple in second order perturbation theory. You can have issues when you look into numerical relativity codes with spherical and spheroidal modes because they're not the same. You could have environmental effects that are known in some cases to lead to the instability of what the quasi-normal mode spectrum itself is. So this is something that might not be relevant for LIGO, but potentially could be interesting for future missions like LISA. And then you have this whole class of horizonless compact objects that at first glance give you a ring down. It looks like a black hole ring down, but at later times so-called echoes, because the horizon for these objects is reflecting at least a part of the gravitational waves. So overall, it's also a very active topic of research, because most of these works are, when you go to beyond GR physics or beyond standard compact objects, usually considering non-rotating systems, because that is much easier to model, and it's much more challenging to see what's happening if you have rotating solutions in beyond GR theories. However, let's keep these things aside. Let's ask ourselves the question, tomorrow we have a great measurement that tells us the quasi-normal mode spectrum, fundamental mode, one or two overtones with very high precision, and we're really confident that these measurements are correct, and they would point to something that doesn't look like Kerr or Schwarzschild. So we would have a situation that we have measured something that doesn't agree with what we think. So now you could ask yourself the question, if we could do that, what would we actually learn? What can we do with that? So we know the no-hair theorems there was something going on, but can we solve the inverse problem? Can we go back and say what a black hole is, what a theory is? So before going into how we are doing this, some comments. So general relativity has some very nice features in terms of the quasi-normal mode problem. So one of them is that the perturbation equations are separable. We don't have additional fields or couplings, for instance, to scalar fields. That is changed. For example, Iris in the previous talk talked about a field where we have additional scalar field. Another feature is that in the study of perturbations of Schwarzschild, you study metric perturbations. There are two sets of perturbation equations, and they are isospectral. And this is also something that is usually broken if you go beyond GR. So how can you do that? There are two general ways of doing this. One is sometimes called phenomenological approach beyond GR, because what you do is you're not starting from a theory, but rather take one of these characteristic properties of GR and try to modify them. For instance, in the problem of QNMs, you have wave equations. We will show you in a second how they look like, and you could modify these potential terms. If you don't have additional fields, there are no couplings, but you can in principle add additional fields, and then you get a coupled system of equations that also changes the QNM spectrum. If you have theory specific, like Iris was in the previous talk, you start from a given action, from a given theory, and then you have to compute the solutions to that. In the QNM problem, you would also have to derive the perturbation equations and solve them. And that's nice because it gives you a clear connection between the observations, let's say the black hole metric, the theory, but it also is a lot of work, and it is, of course, limited to the theory you considered. So let's come back to this question. I assume we have these QNMs, and let's ask ourselves the question, what can we actually learn? For instance, can we recover the effective potential that describes the perturbations? Could we recover the presence of coupling functions, if there are any, not by the fields themselves, but in the way how they change the QNM spectrum? Could we probe something about the underlying black hole metric if it's not Schwarzschild or Kerr? And how do the uncertainties that we have in the QNM spectrum and the fact that we will not measure infinitely many modes, but a handful if we are really, really lucky and promising in the future, how does all of this impact this? And another question is, what is actually something robust that you can extract? So for instance, in solar system type of tests, we have this Boston-like expansion. So if we have modifications to the potential or to the coupling function or to anything that goes like typical PN term, can we actually constrain the individual contributions, or can we not? Is this something robust? And some of these questions were studied by collaborators of mine in other works. For instance, in the first paper I read here, we look at parameterized black hole metrics and how we can use QNMs to constrain their parameters in a toy problem setup. And this other work with Nicola Franchini again, we look into this problem of reconstructing coupling functions if you change the QNM spectrum and also the potential. So what I want to do here and what we did in this paper is to use this framework here. So I will guide you through the equations. Equation 1 is a wave equation, and it's written in a form that if you are in a standard GR case, phi, here is a vector, that would contain your axial and polar perturbation fields. And this potential term V here is a matrix in this equation where the diagonal terms are described by the GR potentials. This is shown here on the left bottom expression. So on the diagonal terms, you would have the standard Rätsch-Wheeler-Zerilli equations, which are the ones that we know from GR. If you have additional fields, for instance, a scalar field, you could add it in this vector. And if you want to couple it to the other fields, you can do this by introducing these off-diagonal terms, which in GR are 0, and there is no scalar field. But in principle, for some theories, it's known in the non-rotating case that you can map them to this framework here. And all these modifications are in equation 3 on the right-hand side, encapsulated in these RH, where RH is the location of the horizon over R expansion, with some coefficients alpha. There's a lot indices going on. So basically, alpha is a huge set of coefficients that could describe the different orders of the coupling function or modifications of the potential. So for a given theory, you might predict alpha, and then you can compute the QNMs, and I'll show you in a second how that goes. Or you can modify the potential in this way. So all non-zero alphas are signs of non-GR physics, so to say. And the framework is very nice, in particular for parameter estimation problems, because if you have ever computed QNMs for a generic potential or coupling function, then you know it's not so trivial. Once you change parameters or the structure of the problem, some of the methods fail or need to be adjusted. And if you want to put this into a, for instance, MCMC code, Markov chain Monte Carlo sampling, where you have to evaluate the likelihood many times, compute QNMs many times, then you need a robust framework that is quick to compute the QNMs. And what these people here, the Cardoso and Ryan McManus, did in these papers is they use this this setup, and they tell you how to get the corrections of the QNMs if you have some small non-zero alpha coefficients, and that's described by equation 4. So basically it tells you if you have some alphas put this in there, and these black coefficients or set of coefficients, they are computed once with respect to the Schwarzschild metric, the Schwarzschild QNMs as the background. So they are provided, and if you put some alpha, you can instantly get the corrected QNM frequency. And that's very nice because it's robust. You put these numbers in and you get instantly an answer. And in this paper here, we have extended this framework to include also the first and second overtones. And how this scales is shown here. So this is the complex plane, and we normalize it with respect to the GR QNMs. And in different colors, we show how the QNM fundamental mode, first overtone and second overtone, change if you go along small changes, for instance, for the RH over R to the power of 2 modification in the potential. This is the blue line here. So you see, if you change the power of this modification, you can go to all points in the complex plane. That's the main picture. So you can describe with this framework potentially many different ways of how QNMs can be modified. So what we did then is we put all of this framework in a MCMC code called MC. And now we will skip some details of the Bayesian analysis because that's, I think, more a technical detail. The big picture here for the QNM problem is sort of independent. So we have two different scenarios that we study. So on the right-hand side here, these are the posterior distributions that we get from such an MCMC analysis, is the following. So we assume that we have measured the fundamental mode and the first overtone and the damping times, basically, the complex numbers with this precision, so percent to up to almost 10%. And then we have put this in MCMC code, and we study two cases. We want to get back all these alphas, but we want to get back these alphas assuming that either you only vary one of them at a time, this is always shown on the left part of the violin plots, or you vary all of them at the same time. And this is a huge difference, as you can imagine. You want to look for one parameter, or you want to look for many parameters. So the left sides are always what you get if you vary one, and the right-hand side is what you get for each of these parameters if you vary all of the others at the same time. The different colors show you different prior ranges, so basically up to which point we allow these parameters to be free. And our priors for all of these parameters were flat uniform. So basically in the case that you are varying all of them, it gives you flat priors back. So you don't learn anything. In the case that you vary one, you can constrain something. In this case, we injected GR, this is the red line here. And that's kind of a trivial test. It gets more interesting when you insert some non-GR things. So here we just, for demonstration purposes, we put alpha 2 and alpha 3 to be non-zero. Then we repeated the same. We varied only one alpha at a time, and you see they're all biased towards the wrong non-GR value besides here and here, but alpha 2 and alpha 3. And in the diagnostic case, if you vary all of them at the same time, again, you get back like prior. So from that, you wouldn't see anything. So you would say you cannot conclude them robustly. So this is not very encouraging because that means you cannot say which power of alpha causes the modification in an agnostic way. That's not surprising because this expansion breaks down if you're close to the light ring. All of these powers are important. So what is much better is if you go back to semi-analytic insights, and one of them is described by the WKB method, which tells you that you can connect the quasi-normal modes of a potential barrier with its derivatives evaluated at the peak. This is shown here with this V brackets. These are derivatives of the potential. So what this means is that maybe you can, instead of getting these alphas, you can constrain the Taylor expansion of the potential around the peak. So to have a fair comparison, what we show here now is we take the priors of flat alphas, we do the projection of what the prior looks like for the potential derivatives. So this is for the height of the potential in the first panel, the second, the third, and fourth derivative, relatively different with respect to GR. So before looking at the data, the right violins are basically our assumptions about the potential. And on the left side, we take the agnostic case, and we vary all of these 10, 11 alphas, and we can see that the posterior for the potential height and the second derivative are very informative. And if you look at the non-GR case, even in that case, you can clearly say there is a non-GR feature if you map it back there. So this is a really cool finding because it shows you that if you have some analytic understanding of the problem, you can construct things that are more robust than just throwing a framework. So this framework is very good to compute QNMs in direct problem, but it's not so good for the inverse one. But what we have shown is that if you look at the Taylor expansion around the peak of the potential, all this complicated maths become very informative. So that's it from my side. Thank you very much. Looking forward to some questions.
Thank you very much. Yes, are there questions? Again, you can either use the Q&A function, raise your hand, or just unmute yourself and speak in this session. Yes, there's a question from Pulami.
Hi, hope I'm audible. As I understand, so this analysis can be used as a testing validity of GR?
So this framework here, for this parameterized coefficients, this is for Schwarzschild so far, because for Kerr, there is much less known about the structure, how to generalize the set of equations. But the problem qualitatively will be similar in the sense that if you have these kind of modifications like Pn powers, you cannot expect to get robust reconstructions. But you can extend WKB also to Kerr. It's not so trivial, but there are also results for that.
Oh, okay. Yeah.
Thank you. We have time for maybe more questions. Yes, there's one from Iris, please.
Hi, Sebastian. Thanks for your very nice talk. I had a question on, it's very nice setup with this theory agnostic way, but how easy would it, or how hard would it be to relate it back to like a specific theory? Can you like just relate these powers of K and say, okay, this would then be describe a certain modified theory I take? Or is that not easy to make that link?
I think it's not easy, and it's not, in a sense, not unique, because if I go back here to this framework, so if you start from some given theory in this direct problem, you will get a set of alphas that depend, for instance, on your coupling functions. So maybe there's just one parameter that describes all of these modifications, but these are many non-zero alphas in principle, or just one. It depends on the case. But if you cannot go back to say which alpha has what value, it's very degenerate. So in that sense, you could match if your theory can predict the QNMs, like performing standard spectroscopy. And you could see, of course, how your theory's coupling function changes the potential, because this is the robust thing that you can see. But directly going back from the results here to coupling functions requires some additional assumptions.
Yeah, okay, so it's really a one-way street, basically.
So it's this framework is a one-way thing to say what it, yeah, exactly. But it's not a limitation of the framework. Like in general, there are some non-uniquenesses in this inverse problem. Even for if you compare Reggie-Wheeler-Zerilli potentials, they're different, but the QNMs are exactly the same. So you could never say which of the potential you are studying in that sense.
Yeah, okay, thanks.
So any other questions? We have time for one short question, maybe, if there is one. Okay, that doesn't seem to be the case. Yes, then let me thank Sebastian again. If there are questions coming up, just use the Q&A and we will answer them online, or use the Oxford abstracts and just post it there. And now we can proceed to the third and last speaker of the session, Andrea Miani from the University of Trento. Please.
Okay. Then, first of all, hi everyone, and I'm here because I want to present you the last search developed in our group, which is Coherent Wave Burst Group, or CWB in short, which is part of the LIGO, Virgo, and CAGRA collaboration. The search aims to detect possible gravitational wave echoes nearby a binary black hole coalescence, and in setting constraints over their amplitude. And this analysis is performed through the unmodeled search for gravitational waves called Coherent Wave Burst. And above are listed my collaboration. And okay, and the outline of the presentation, first of all, there will be a very brief introduction trying to address the question why are gravitational wave echoes interesting. Then I will provide very little overview about our method for searching echoes. Then there will be an overview of our results. and then also partial comparison with previously published gravitational wave echo searches. And I will end with a conclusion. And so if we start by asking ourselves why we need to search for gravitational wave echoes. First of all, gravitational wave echoes are periodic gravitational wave pulses possibly emitted by compact binary coalescence remnants. And if we look at the plot on the right, there is the amplitude of gravitational waves as a function of the time. And as you can see on the left, there is the last part of the spiral merger and ring down of our binary black hole signals. And different from the expectation from general relativity, in the post-merge, you can see this periodic bump of perturbed space-time. To these bumps, we address the name of echoes, and they are predicted by alternative models to black holes from the general relativity theory, and these alternative models are called exotic compact objects. And it is interesting to search for gravitational wave echoes because they allow us to probe the general relativity theory, meaning that it is possible to try to solve the black hole information paradox, as well as one can also investigate the black hole nature or a possible exotic state of matter, since this gravitational wave echoes should arise from compact objects which are not black hole indeed. And how we actually search for this kind of signals? First, we use an unmodeled search, and we need to construct both our background statistic or null hypothesis statistics and also our signal statistics. First of all, we need to have a detection of a binary black hole gravitational wave signals, and then we can apply our search, which is then a follow-up search using CWB. So we select the data we want to analyze, then we perform a two parallel analysis, one in order to recover our background, the other one to recover our signal distribution. And basically they are the same kind of injection over the same data period with the same binary black hole signals taken from the posterior samples for the interested event. But in the signals analysis, we also inject in the post-merger our gravitational wave echo proxy. Here we use elliptically single Gaussian signals because for our analysis, which is a modeled, it is important to have an energy access. And as we will see sooner, the morphology of the echo proxy is not so relevant. And then by analyzing these two analyses, we can infer our null hypothesis statistics and our signal one. The quantity we estimate are calculated inside a post-merger time window, which is highlighted in this light blue region on the plot on the right. This quantity, the major quantity, are the reconstructed energy inside the window, the signal-to-noise ratio, and then it is possible to estimate also the detection probability and the false alarm probability. The formula are identical, but the detection probability is estimated over the signal distribution, while the false alarm probability over the background one. And due to the working procedure of this CWB, we need to set up a blind time after the coalescence time, meaning that we cannot extend our post-merger time window starting from the coalescence time, but we need to avoid at least 50 milliseconds after the coalescence time. And
in this exploratory study, we decided to implement two possible setups. So if the arrival time of the first echo pulse is predicted to be within 200 milliseconds from the coalescence time, then our blind time is of 50 milliseconds and the post-merger window time duration is of 300 milliseconds. On the contrary, if the arrival time of the first echo is predicted to be greater than 200 milliseconds, we use a blind time of 200 milliseconds indeed, and a post-merger time window of 1 second. Now, the first test we had was to be sure that our analysis performances are independent from the morphology of the echo-like proxy. And in the plot on the right, you can see the detection probability of a signal in the post-merger as a function of the signal-to-noise ratio of injected signal-to-noise ratio within the post-merger time window. And we tested different morphologies, for example, a single high mass binary black hole signals or different elliptic Ising Gaussian proxy at different central frequencies, or even white noise burst. But the performances of the search remain stable, and notably, although all of these results are provided with 5% of false alarm probability, and we had a detection probability of 50% around an injected SNR of 5, so quite a low value. And now we have analyzed subset of all the gravitational wave signals emitted by binary black holes detected during O1, O2, and O3. The results from here onward are provided in by analyzing the injected HRSS of the echo-like proxy. Here there is a plot of the detection probability for actual binary black hole signals as a function of the injected HRSS. And first of all, there is here are not reported all the analyzed events, but only a very limited sample for each of the observing run from LIGO, Virgo, and Kaga collaboration. And you can notice an increase in the performances of our search, which are related to the performances increased by the detectors of the collaboration. And nevertheless, in O3, we are able to reach a detection probability of 50% for a value of injected HRSS around 1.7, 1.8 in 10 to minus 23 per square root of Hertz, which is a very interesting result because the CWB standard search for a modeled burst signals, which inspires our methodology, reaches a detection probability of 50% for value of HRS about 8 in 10 to minus 23 per square root of Hertz. This is, well, it is not a one-to-one comparison because in that estimate of value, they use a single pulse and they had a very large amount of data available. But nevertheless, we confirm that our performances are very interesting. Then maybe one of the more interesting results is the test of the null hypothesis. So for all the binary black hole we analyzed, we try to answer the question if there is anything interesting in the post-merge. And to do so, we estimate the p-value of the null hypothesis by calculating the signal-to-noise, the reconstructed signal-to-noise ratio for the source signal. And in this plot, there is the ranking statistic of the p-value. The blue dots are, each one represents the results for one event. and the red line corresponds to the 50% discovery rate, and we arbitrarily decided to set interesting region for first discovery rate below the 10%. And as you can see, only 2 events, GW190701 and GW200224, results to have an excess of energy which is worth to be investigated, but in the end it came out that this energy excess present in the post-merger is due to only some noise disturbances. So our results are very well in agreement with the previously published results from the testing jar paper from LEGO Virgo collaboration. And now coming to the upper limits on the amplitude for this gravitational wave echo signals, we recovered this kind of results by analyzing the confidence belt we can construct over the injected HRSS, which is plotted as a function of the reconstructed signal-to-noise ratio inside the post-merger window. And once we have this 95% confidence belt, which is the blue area in the plot on the right, we can draw a line for the corresponding on-source value of the signal-to-noise reconstructed signal-to-noise ratio, and extrapolate the maximum value for the eco-like proxy injected HRSS. This value is then compared with the corresponding mergering down HRSS of the primary, and the ratio for our setup is well approximate. It can approximate very well the predicted amplitude parameter for ecos, which is A. And as you can see, as far as the binary black hole event, the analyzed binary black hole event is high mass 1, high mass 1, yes. The amplitude is limited below a value of 0.4, let's say, with our best upper limit, which reach a value of 0.1, and which can be translated in an HRSS upper limit of from 1 to 4 in 10 to minus 23 per square root of Earth. And this upper limit on A worsen if the binary black hole signals involves low mass components, as it is for GW200225 and GW190814. The value I've reported here the value of GW200224, but be careful that this value is biased by the noise glitch in the post-merger, so it's not a reliable one. And how our search performs with respect to other eco searches within the literature? Well, the CWB echo signal search, by looking at the result we obtained for GW150914, displayed that if the signal-to-noise ratio within the post-merger windows is about 12, we almost ensure a detection probability of 100% with a first alarm probability of 0.1. On the contrary, if the SNR is around 8, we still have a detection probability around 95–99%, always at a first alarm probability of 5%. And as we have seen, the upper limit on A are around 0.21, which can be translated into an H value, so an amplitude value of the echo of 2.3 in 10 to minus 23. And these results are in agreement with some of model search for ecos, as well as model independent search for ecos. For example, the one by Zhang et al., which has comparable signal-to-noise ratio performances, or also the two model dependent search by Rico or Westerwak. And So in conclusion, I just want to highlight the fact that our unmodeled search for gravitational vehicles delivers comparable results to the if compared to other searches in the literature, and it has a good performances for let's say possible signals in the post-merger which retain a signal-to-noise ratio around 5, so we are able to detect them, and the upper limits on A, we can say that up to now it is possible to say that if some signals are present, they can be detected only if their amplitude with respect to the one of the merger is greater than 0.35. And with this, I've concluded my presentation, and I want to thank you all for the attention.
Thank you for the nice presentation. So, are there any questions? Yes, there's a question from Sebastian. Please go ahead.
Hey, Andrea. Thanks for the nice talk. It's really important, yeah, what you do to quantify that some of these claims that there's new physics and so on is not really due to noise. I wanted to ask you whether you plan or how much you can use the amplitude balance to say something about the reflectivity of the object. If there is some, you know, that some people model not perfect reflection at the horizon, but some frequency dependent maybe, or you know, something more complicated. So is there a way to use your amplitude posteriors to say something about these properties?
Yes, indeed, that could be a possible upgrade of this search, because I know that there are several papers about how it is possible to how gravitational vehicles are related to the compactness and the reflectivity for this exotic compact object. And at first, we will try to relate our amplitude upper limits on the predicted waveform for ecos expected from that kind of theories, or well, let's say model, because it is more correct to say model. And but then, which is a major upgrade and probably a more realistic one, we can also try to inject in our data that specific model. So if a group or someone wants to provide us some waveform related to a model with let's say distribution of possible value for the reflectivity value as well as compactness, in order to have a posterior sample for possible gravitational wave echo signals, then we can inject that specific model and obtain very focused results, always on upper limits on A, but also we are implementing morphology estimation of the morphology of the echo, and so we can provide more detailed and focused results for that specific model.
Okay, that sounds very good. Thanks.
Thank you.
Thank you, Andrea. Well, if there are no urgent questions, then thanks again, Andrea, for answering also the question and for the talk. And I would like to thank all the speakers of the session for their very nice talks, and everybody who joined us and participated in this session. So thanks a lot. With that, the only thing that I still want to say is that we continue this afternoon here at the Amaldi 15 at 4 in European summer time, and with talks on probing the universe expansion with multi-messenger astronomy, as well as collaboration on global and local scales, and artificial intelligence and machine learning. So I hope to see all of you later. And with that, thank you and goodbye.